Thank you, Matt. So thanks again, everyone, for joining our webinar for airflow control devices. Once again, my name is Abdul. I am the engineer technical sales contributor at Antec Controls. So the goal for today's webinar is to mainly introduce you to the basics of airflow control technologies and introduce the differences between electronic and pressure independent air valves and mechanical pressure independent air valves. So this will include things like venturi valves, high accuracy terminal units, and VAV boxes. So we'll be discussing those air valve technologies and giving some recommendations based off of the applications they are best suited for. For today's learning objectives for this webinar, we're going to be covering the differences between electronic pressure independent and mechanical pressure independent airflow control devices. We'll be describing the differences between the airflow measurement technologies, defining some speed of response terminology and how they relate to airflow control devices. And then lastly, we'll finish off by identifying some design requirements for electronic pressure independent air valves and mechanically pressure independent air valves. So the agenda for today's webinar will include starting off by discussing the airflow control devices, again, highlighting the differences between electronic and mechanical pressure independent valves. We'll then be discussing speed of response, some design consideration, maintenance requirements or considerations, and then we'll finish off our presentation with the summary and then open the floor for any questions you guys may have. So to go ahead and get started, as we've talked about already, this webinar will be mainly focusing on the three valve technologies in front of you. We'll be discussing legacy terminal units, high accuracy terminal units, and venturi valves. When we talk about these three valve technologies, we really want to start defining some criteria where we can better differentiate them between each other. So in this case, we're going to define legacy terminal units and high accuracy terminal units as being electronically pressure independent. This means these valves are directly measuring and controlling the airflow. On the other side, we have venturi valves, and we're going to define this valve as mechanically pressure independent. So this air valve is going to be metering the airflow, and we're going to talk a little bit more about both of those very shortly. So with that, we're going to go ahead and get started with talking about electronic pressure independent air valves. So what are electronic pressure independent air valves? These are valve technologies that measure the actual changes in the controlled variable. In this case, this is airflow, and then actuating a change in order to control that variable. So in this case, if we look at the graphic on the right side, we have our standard legacy terminal unit. And essentially what we're having here is a repeated loop of being able to sample the airflow, compare that airflow with the set point required that we're controlling to, calculate and reposition the damper in order to bring about a change to get that sampled airflow closer to set point, and then finally adjust that damper and then resample the airflow. So this loop essentially will continuously happen. So with these electronic pressure independent air valves, we would expect that the actuator will move when there is either a change in the airflow target or if there's a change in the duct pressure. So once again, these will include our terminal boxes or our high accuracy terminal units. So with this, we're going to go ahead and get started by talking about our first air valve technology, which is the terminal unit or your classic VAV box. I'm sure a number of you guys have a lot of experience with this valve technology, so we'll keep this section a little bit brief. Essentially, with the classic terminal unit, this is a direct airflow measurement utilizing an in-stream sensor. Now, depending on the sensor you have at the inlet of the valve, this could typically be measuring velocity pressure, and we're utilizing that velocity pressure to calculate airflow, and then again bring about the change to the damper and redo that loop. So what makes up the velocity pressure? Well, velocity pressure is difficult to directly measure. So in order to calculate velocity pressure, we're typically going to be measuring total pressure and static pressure and getting us that velocity pressure reading. Now, with terminal units, we're typically going to see about a 6-to-1 turndown ratio. Again, depending on the valve size you select, the turndown ratio will slightly vary. And the other requirement you're typically going to see with your classic terminal unit is the requirement for straight duct. Since we're measuring velocity pressure, it's really important to have stable, non-turbulent flow across the sensor. So in this case, you're often going to see mandated straight duct at the inlet and the exit of the valve to ensure we can get that laminar flow across the sensor. So looking at a sample specification, sample airflow for these valve technologies, the biggest thing we're going to highlight here for the classic terminal unit is the minimum operating pressure. Due to the shape of the terminal unit being cylindrical and really just having that sensor at the inlet and the damper at the exit, terminal units are very low static pressure devices. What this means is you require very minimal amount of pressure in order to achieve the airflows that you're looking for. Once again, we'll look at that side, we have the turndown ratio. So again, the turndown ratio is just a ratio between your minimum flow and your maximum flow. So as we introduce the other valve technologies, we're going to start to compare these between each other, between the turndown ratio and that minimum operating pressure requirement. So we're going to go ahead and start to talk about our first air valve technology, which is our high accuracy terminal unit. Now, the real importance here that we're going to really highlight between the differences of your standard accuracy terminal unit and your high accuracy terminal unit is in the name. A high accuracy terminal unit allows us to achieve and control airflow with much more and much better accuracy. So depending on the technology you're looking at for that high accuracy terminal unit, how we control airflow can change. We may utilize velocity of pressure, vortex shedding, thermal dispersion, or static pressure. The valve technology we have on the left side does utilize static pressure, so we'll utilize this as an example of talking about high accuracy terminal units. So looking at this high accuracy terminal unit, the biggest thing you're going to see different between this valve is that shape. We no longer have that cylindrical shape. Instead, we're utilizing this venturi shape. What this venturi shape allows us to do is compress the airflow from the inlet of the valve to the throat of the valve. And what this does is it amplifies the pressure drop that we can measure and control airflow. So this amplification of the pressure drop now allows us to do two things. First, allows us to increase the turndown ratio, which means this valve can now achieve lower flows that we can still control too accurately, and likewise achieve a bit of a higher flow range. So you're going to see here about 11-to-1 turndown ratio. The second thing this allows us to do is, depending on the technology you're utilizing, in this case being static pressure, we don't require any straight inlet or outlet duct run requirements. Again, this is really important for the fact that it simplifies when you're having to set up your duct runs, things like that. If there's a lack of availability of space, we now gain the ability of minimizing the requirements for the installation. And then lastly, depending on the technology you're using, again, in this case, we're referring to the static pressure. The static pressure readings allows us to be a little bit more resistant to contamination. And the reason why is because we now have the static pressure ports facing downstream of the airflow direction, which gives us just natural protection from lint, dust, and other contaminants causing issues with the reading. So as we kind of summarize here again, biggest benefit we're going to get with the high accuracy terminal unit is in the name. We're just getting much more accurate readings across the entire flow range of the valve. So typically you're going to see these valves operate within 5% accuracy across the entire measured, the entire published range, as you see here in front of you. Additionally, because we're utilizing this venturi shape, we're amplifying the pressure drop. That allows us to now control much more accurately at the minimum flow range, as like with the maximum flow ranges. Now, this does come at a little bit of a cost due to the shape of the valve. This does amplify and increase the minimum operating pressure in comparison to a terminal unit. So typically, you're going to see these air valves operate at 0.3 inches at the maximum flow ranges. If you're looking at the mid-range flow ranges, you're typically going to see that again between 0.15 to 0.2 inches of pressure for the minimum. The second valve technology we're now going to talk about is the mechanical pressure independent valves. I just want to highlight here once more the valve technologies we've talked about so far. Those will typically include measuring the airflow and then having a damper to control based off of changes in the pressure. With this valve technology, we're now essentially having a mechanical response to the changes in pressure. So what this means is we don't necessarily have a direct link between the value of the controlled variable, which is in this case airflow, and the controller. Additionally, we're no longer relying on direct airflow measurement for these valves. Valves that are mechanically pressure independent essentially decouple the effects of pressure fluctuations inside the valve to the airflow going through the valve, or the airflow we're controlling through the valve. So because of this requirement, because of the fact that we have that decoupling of pressure and airflow, what you're going to see with a mechanical pressure independent valve is that your actuator is only moving when there's a change in your airflow target, not when there's a change in your duct pressure. So in this example on the left side here, we have a venturi valve, which is a mechanically pressure independent valve. And with the venturi valve, whenever there's a change in airflow target, we're going to expect the actuator to move. When there's a change in duct pressure, we're going to expect the cone spring to move. So essentially with this venturi valve, we have two mechanical operations going on. The first mechanical operation is that cone spring inside the valve. Whenever there's a fluctuation in that duct static pressure, that cone spring is reacting instantaneously to that change. It's essentially a force mass balance equation with the spring inside the valve and the fluctuating pressure. The second mechanical operation we have is the controller, actuator, and that lever arm. So whenever the airflow set point has to change, we would expect that the actuator will adjust the position of the lever arm, which will then allow us to change the airflow set point. We'll talk about that again in a few slides. So due to the fact that there's no ability to relate pressure inside the valve to airflow, what we instead have is a relationship between the control arm position of the valve and the flow going through the valve. So typically with these venturi valves, what you're going to have is robust factory testing to ensure high accuracy and high repeatability to ensure that whenever the control arm position moves, we're getting the same airflow through the valve. So at the factory, what we're doing is we're taking the control arm position, which is measured through a precise potentiometer. By measuring the position of the control arm through the potentiometer, we can calculate and determine what the airflow going through the valve is. So in order to ensure that repeatability, the factory is going to be testing or should be testing these valves through accredited airflow stations to ensure high accuracy and high repeatability. So when that valve is operating on site, we're still able to maintain that 5% accuracy without having to rely on a direct airflow measurement, but instead being able to rely on the control arm position measurement from the potentiometer. So with this graphic here on the left side, you're going to see here when airflow enters into the valve, as that pressure fluctuates, that cone spring is going to react. When the pressure increases, the cone spring is going to sit further inside the valve, limiting the available area for airflow to get around the valve. It's the same on the opposite end. When the pressure decreases inside the valve, that cone spring is going to relax, sitting further outside the valve, increasing the effective airflow area, resulting in the same constant flow. So whenever we expect there to be a change in pressure, we expect the cone spring to make that reaction for us. And whenever there's a requirement to change the airflow set point, we'd expect the actuator to adjust the lever arm position, and we rely on the potentiometer to determine the airflow going through the valve. So again, just to summarize, with the venturi valve, we're relying on electronic flow feedback through the potentiometer. This air valve technology is mechanically pressure independent because we have a cone spring inside the valve, essentially allowing us to control airflow mechanically independent of the pressure fluctuations. Because the air valve technology doesn't have any sensors inside the airstream measuring and calculating airflow, we actually can now have a much higher turn down ratio, around 20:1, depending on the valves that you're selecting. Again, what this means is, assuming, let's say, this valve can control to 100 CFM, we now have the ability of controlling from 100 CFM all the way to 2000 CFM. Additionally, because there's no sensors inside the airstream calculating airflow, the effect of turbulence won't affect the controllability of this valve. So there's no requirement to have any straight inlet or outlet duct run. And then lastly, with these valve technologies, the biggest thing to know, to ensure we can maintain that mechanical pressure independent nature, we have to ensure that we have at least the proper amount of pressure through the valve to get us that compression through that spring. So with these valve technologies, the monitoring you're going to get is the pressure measurement, the pressure monitoring through a high and low pressure port. I'll talk about that later in this presentation. So as we kind of highlighted here earlier, whenever we expect pressure fluctuations inside the valve, we expect the cone spring to react. So at 1 inch of pressure, we'd expect the spring to expand, increasing the airflow area. And then when the valve suddenly starts to operate at 3 inches of pressure, assuming the airflow set point stays constant, we'd assume the spring to compress, decreasing the airflow area, resulting in the net same amount of flow going through that valve. So assuming the airflow remains constant, we're going to only expect the cone spring to react to the changes in fluctuation of pressure, but the overall position of that center shaft and the lever arm is going to stay the same. So looking at the data a little bit here, we'll first talk about the medium pressure venturi valve, and then we can highlight the low pressure afterwards. So again, typically with the medium pressure venturi valve, you're going to see the highest turn down ratio available. But again, the requirement, in order to maintain that 5% accuracy, we're going to have to ensure we're meeting the operating pressure range of that valve. So how the operating pressure range of the venturi valve operates is very different from your classic terminal unit. From your classic terminal unit, you'd expect your minimum operating pressure to be measured at your damper blade full open, as tested in accordance to ASHRAE 130. But for a venturi valve, instead, what you're going to get is a pressure range. So as long as this valve is operating within this pressure range, we can guarantee that 5% accuracy. So for a medium pressure venturi valve, that pressure range is between 0.6 to 3 inches. And then for a low pressure venturi valve, it's going to be between 0.3 to 3 inches. So just to kind of give you an example, if you have a size 8 venturi valve operating at 700 CFM, if you can maintain at least 0.6 inches of pressure across the valve, we can maintain that 5% accuracy. On the opposite end, this same valve is now operating at 35 CFM. we can still guarantee 5% accuracy with that valve operating at 3 inches of pressure. So to give a little bit of an example to kind of, again, compare the differences between these valve technologies, we're going to go ahead and show you the difference between system stability with electronic pressure independent valve and a mechanically pressure independent valve. So in this example here, we have a damper style valve operating all at 700 CFM, being served by the same fan. So if, let's say, the middle valve suddenly starts to operate at reduced airflow, let's say 200 CFM, we'd expect that the fan would now have less area to pull flow through, so we're suddenly going to see an increase in pressure. If there's no controller or actuator to adjust those damper blades as that static pressure fluctuates, we would then expect to see the airflow from the top valve and the bottom valve to increase accordingly. So you kind of have to have a controller and an actuator on all 3 air valves in order to give us that damper fluctuation, that damper change when the static pressure increases. On the opposite end though, we have the mechanical pressure independent valve. So here again, same example, we have 3 mechanical pressure independent venturi valves, all operating at 700 CFM. If that middle valve suddenly starts to operate at reduced flow, let's say 200 CFM, again, we would expect the pressure to increase because the fan has less potential area to pull flow through. The difference here is because we're utilizing that mechanical pressure independence, because we're utilizing that cone spring, whenever the pressure fluctuates, the cone spring is going to immediately react to that change. So in this case, we can provide these 3 venturi valves with no controls, no actuators, have them mechanically set to a constant flow, and we would still expect them to be able to control to the flow set point we would expect. So now that we've talked about the valve technologies, we're going to go ahead and start talking a little bit about the speed of response. Speed of response is very important to understand because if we're looking at these valve technologies in the context of critical space applications like hospitals and laboratories, maintaining safety is very, very important. But there's always a little bit of confusion regarding the speed of response, mainly for the fact that there's so many different definitions we can have for speed of response, and they're all going to have slightly different requirements. So the main 5 types of speed of response we're going to talk about are actuator speed, the speed of response to a change in duct static pressure, the speed of response after a change is introduced, the speed of response to a control signal, and then lastly, the speed of response of the fume hood base velocity. So with the first speed of response, we're going to talk about the actuator speed. So the thing we're looking at here mainly is the stroke time for the actuator. How long does it take the actuator to go from the minimum position all the way to the maximum position? So typically in these critical space applications, you're going to see 2 types of actuator speeds being utilized. You're going to see standard speed actuators and high speed actuators. So with standard speed actuators, these are typically going to be your healthcare and sometimes pharmacy applications. These are applications where there's no requirement for high acting speed of response due to user safety or due to governing regulations. So this is very much your typical HVAC application in the sense that we're really trying to have stability here. We want stable readings to give us the accuracy we're looking for. On the opposite end, we have high-speed actuators. So again, these are the applications that require that fast-acting speed of response. More commonly, you're going to see these utilized in laboratories. So again, for a fume hood, that requires between 1 to 3 seconds or 3 to 5 seconds speed of response. Being able to achieve that containment as required, we're going to have to utilize a high-speed actuator. So depending on the model actuator you're looking at, these are typically going to range between 2 seconds to 4 seconds depending on the model. So the second speed of response we're going to take a look at now is the speed of response to a change in duct static pressure. So here we have on the left side, we have our electronic pressure independent valve. On the right side, we have our mechanical pressure independent valve. So with an electronic pressure independent valve, our speed of response is really going to be dependent on how fast can we measure the change in pressure and then adjust the damper accordingly to that change, and then remeasure to see if we're maintaining our set point accurately. So with this valve technology, you're going to get a quick speed of response, assuming you're utilizing a higher accuracy terminal unit. Standard accuracy terminal units can get you adjustments due to the change in the static pressure as well. On the opposite end though, with the mechanically pressure independent valve, you're really going to get that instantaneous change when there's fluctuations in that duct static pressure. Because that cone spring inside that valve is mechanically regulating due to the changes in the pressure, because there's no controller telling that cone, that spring to make any adjustments, you're going to get by far the fastest response, which again, there's really not much that can beat that instantaneous response to that change in pressure. So next, we're going to talk about the speed of response after a change is introduced. So ANSI Z9.5 states that for most operations, 10 seconds is an acceptable time to achieve the desired area pressurization. But again, a hazard application should still be conducted to determine the acceptable time. So what we're really talking about here is when we're working in these critical space applications, we want to ensure that we can maintain the overall pressurization within 10 seconds after a change is introduced. So if a fume hood is opened or a door is opened or closed, can we still maintain the required pressurization that require containment within 10 seconds? Next, we're going to talk about the speed of response to a control signal. So here, it's the amount of time for the controller to process a change in information before it enacts a change. So for your classic electronic pressure independent valves, like the terminal unit and high accuracy terminal unit, this is really going to be dependent on that control loop between how fast can we measure the airflow, how fast can the controller compare that to set point, adjust the damper, and remeasure that variable. On the opposite end, for the venturi valve, the mechanically pressure independent valve, this is going to be a lot faster due to the fact that when the actuator adjusts, we essentially are just controlling the lever arm position to the predetermined factory defined set point. The last speed of response we're going to talk about here is the speed of response for the fume hood face velocity control loop. So for the fume hood face velocity, there's a number of different standards out there that defines the acceptable response, the acceptable containment for these hoods. The two that we're going to highlight here are ANSI Z9.5 and ASHRAE 110. So ANSI Z9.5 states that the VAV control system must be capable of fast, accurate, and precise adjustment of flows without experiencing any major overshoot or undershoot. So in this case, having air valve technology like your higher accuracy terminal unit or your venturi valve gives us much more flexibility in meeting this requirement. Additionally, a response time of under 5 seconds after initiating the sash movement or a change in operating mode is what we're typically considering acceptable in most operations for these fume hoods. ASHRAE 110 additionally will also dictate what's the speed of the sash movement. So in this case, ASHRAE 110 says that when you're performing these tests, the sash shall be moved in a smooth motion at a speed between 1 to 1.5 feet per second. And additionally here, it also states that we're typically looking to maintain a steady state value of 90% of the average. So next, we're going to go ahead and talk about the design consideration for these electronic pressure independent valves and mechanically pressure independent valves. Now there's a lot to really consider here for design considerations. So for the sake of time, I've only really highlighted one or two for each valve technology. So for the electronic pressure independent, one of the design considerations you want to keep in mind is the minimum operating pressure drop. The minimum operating pressure drop is that static pressure drop for the terminal when it's operating at its maximum scheduled flow rate with the damper blade wide open. Again, this is typically tested in accordance with ASHRAE 130. Now, what this really tells us, the minimum operation pressure drop tells us, is it's the worst case static pressure drop through the terminal that the fan will have to provide or account for. So when you're doing your critical path calculations, this gives you the basis to ensure that that critical path valve still has sufficient pressure to operate and control for airflow. So typically, what you're going to see for a high accuracy terminal unit is that it may operate at a higher pressure drop in comparison to your classic legacy style terminal unit. But what we gain now is the 5% accuracy across the entire published flow range. So as long as we can meet the minimum operating pressure drop and we can control for the airflow set point we're looking for, we're now gaining that 5% accuracy. So on the bottom here, we have just a sample schedule for an air valve that's been tested in accordance to ASHRAE 130. So if we're looking at a size 108 air valve that we had to have operate at 550 CFM, what this table tells us is that we're going to require a minimum operating pressure drop of 0.15 inches. What this means is if we just want to have the capability of reading 550 CFM through our 8-inch valve, we have to be able to maintain 0.15 inches with the damper blade being fully open. Now, since the damper blade is fully open, this doesn't give us any controllability at this set point. So if we want to be able to control to 550 CFM, we're going to have to allow for some tolerances a little bit more than 0.15 inches. This lets the damper blade close a little bit, and now we can control to 550 CFM. For mechanical pressure independent air valve, we are going to have to consider this a little bit differently. So with the design consideration with the mechanical pressure independent valve, there is no relationship between the airflow and the valve's operating pressure. There's no way for us to calculate what airflow the valve is at, what pressure we're going to require. So again, the variable of airflow and pressure are fully independent from each other. So we don't have any way to correlate that. So what this means is that for a venturi valve to operate and control correctly and accurately within the full minimum to maximum scheduled airflow, the venturi valve has to maintain sufficient pressure across the valve. So again, as we mentioned, for a low pressure venturi valve, we're going to require at least 0.3 to 3 inches. And then for a medium pressure venturi valve, we're going to require at least 0.6 to 3 inches. So typically as a design engineer, what you're going to want to allow for is a little bit of a buffer to ensure that the pressure is within the applicable specified range while the valve is operating at the maximum design flow. So again, what we might want to do for a low pressure venturi valve at our maximum scheduled or designed flow rate, we're going to want to assume that the valve is going to require at least 0.6 to 0.7 inches of pressure, for example, to give us a bit of a buffer. So if anything on site were to occur due to extra duct runs, things like that, we still have a bit of a buffer to control accurately at the maximum designed flow rate. So the last thing we're going to talk about here before we open the floor to questions is maintenance. Now, there's a lot that you're going to really want to consider for maintenance when you're selecting your air valve technology in these critical space applications. So again, I've just highlighted three of the three potential considerations when you're starting to talk about maintenance requirements for these valves. There's a lot more considerations you're going to want to keep in mind, but for the sake of time, we're just going to highlight performance monitoring, contamination prevention, and life cycle servicing. So some things you're going to want to consider when you're discussing performance monitoring as a maintenance requirement for these valves is potentially what are the capabilities to integrate the air valve technology with our building management system for real-time monitoring and alarming. For contamination prevention, you may want to consider, does this valve technology give us some resistance to contamination for lint, dust, and other contaminants during normal operation of the valve? And then lastly, for life cycle servicing for this valve, what's the proactive service interval we're going to want to have for the lifetime operation of the valve? Now, when we're talking about, again, these critical space applications, like a healthcare application or a lab application, we really also want to consider the time and the effort. We want to ensure that these critical spaces can stay online for as long as possible and minimize interruption as best as we can. So first, we're going to talk about performance monitoring. So again, in this case, we're really just going to highlight one technology for each. So in this case, for electronic pressure dependence, for performance monitoring with a terminal unit, you're typically going to see some velocity pressure feedback. So again, with your typical standard accuracy terminal unit, the sensor on your inlet may include an averaging pitot tube or a cloth flow sensor. And these are devices, again, that are going to calculate the help us calculate the velocity pressure. Typically, with the controller you're going to have, the controller is going to take the velocity pressure, calculate it to airflow, and then have it reported to the building management system. Something to highlight critically, again, is typically with your standard accuracy terminal unit, you're only going to be able to achieve 5% of accuracy in a constant volume application. So if you expect this terminal unit to modulate and be able to control to a wide degree of different set points, you will lose the accuracy of 5%. You're just not going to be able to maintain that. On the other end, for a high accuracy terminal unit, we're going to highlight the static pressure feedback as a performance monitoring consideration. So again, the advantage of having to measure static pressure is the ability to remove velocity pressure from the equation. So we talked about velocity pressure is a little bit more sensitive to fluctuations in the duct. It's going to require more laminar flow. So in this case, it's the same idea. We're going to have a controller measure the static pressure, calculate airflow from that static pressure, and then go ahead and report it to the BMS. The advantage we get though with performance monitoring with a high accuracy terminal unit is the accuracy. So in this case, we're going to gain the ability to be accurate within 5% across the entire airflow range of the valve. So performance monitoring for venturi valve is typically going to involve two considerations. So the first one we're going to talk about is the electronic flow feedback. So the electronic flow feedback allows us to control and report airflow without the need to have that airflow measuring station. As you can see at the image on the right, I've highlighted the potentiometer, that high accuracy precise potentiometer that's measuring the position of the lever arm, which we're then allowed to then calculate what the airflow of the valve is going through based off of the factory calibration that's been done with this valve. The second type of performance monitoring you're going to want to consider for a mechanically pressure independent venturi valve is the operating pressure feedback. As I highlighted a number of times already, the venturi valve will only be accurate to 5% of the flow range when it's operating within the design pressure. So if we're no longer operating at design pressure, if it's too low or if it's too high and it's outside of the published range, we no longer can maintain that same 5% of accuracy. So in this case, it's really important for that venturi valve to be able to measure and report that operating pressure so you can now monitor and alarm for it through your building management system. So all of these performance monitoring really feeds very nicely to us talking about ASHRAE 90.1. So what ASHRAE 90.1 is really dictating is the energy consideration for your building system. So specifically regarding your VAV, your variable air volume valves, ASHRAE 90.1 states that your static pressure set point shall be able to be reset based off of whatever valve is requiring the most pressure. So essentially, we should have provisions to be able to reset the set point until one of our zone dampers are very nearly or wide open. This, as long as we're controlling the fan and reducing the fan set point based off for critical path valve, we can now start to save some energy by having that fan operate at a lower set point. So to enable this fan static reset as dictated by ASHRAE 90.1, the controls that we're providing for these air valve technologies should either have the ability to monitor the zone damper position or provide another indicator in the need for static pressure. So typically for your high accuracy terminal units or your electronic pressure independent valves, we're going to be monitoring the damper position through a actuator position feedback. So we're monitoring that zone damper position directly through the actuator position feedback. For a venturi valve, we're going to be able to want to monitor the static pressure through the high and low pressure ports. So again, we can actually control the fan and still enable a fan static reset by monitoring the pressure for that venturi valve from that high and low pressure port. So next, we're going to highlight the contamination resistance. So the contamination resistance for a high accuracy terminal unit is really going to be dependent on the valve you've selected and the sensor design. So there are a number of different configurations available currently. So the main one I'm going to talk about is the high accuracy terminal unit provided by Antec Controls. So this high accuracy terminal unit measures the differential static pressure utilizing pressure ports facing downstream of the airflow direction. So what this gives us is the ability to reduce the risk of lint and other airborne particulates affecting that control or accuracy of the valve during normal operation. When we bring this into the context again of a lab application or healthcare application, having to go up into the valve to clean it out, things like that, can affect operation for the facility and they potentially include additional costs. So having the ability of natural protection or minimization of that risk of lint and other airborne particulates affecting the valve is really important. On the other end, for venturi valve, well, a venturi valve, because we don't have any sensors directly inside the airstream measuring airflow, we have already a lot more natural protection from contamination. So the only thing you typically should be measuring directly on a venturi valve is the pressure. So now we just have to consider, well, what is the risk for those pressure ports from getting clogged from lint, dust, and things like that? So first, because these pressure ports are what we call low profile, what this means is they're not sticking into the airstream directly. They're very much low profile installed at the top of the valves. This gives us just natural protection again, which makes it really hard for lint, dust, and other contaminants to clog those pressure ports. Additionally, because that venturi valve typically operates at a higher pressure, the higher velocity actually pulls the dust or lint directly through the air valve. So we'll typically not even see any buildup. In that case, it'll typically just get passed directly through the valve. So the last consideration we're going to talk about here before opening the floor to some questions is the life cycle servicing. So this is a very complex topic in aspect of selecting an air valve technology purely based off of cost can actually have some knock-on effects due to potential higher maintenance costs over the life cycle of that air valve. So I understand that some projects are just naturally going to be restrictive on cost, and that's the driving factor. But if you're working on a project where cost isn't the driving factor, we really should take into consideration what that overall life cycle servicing is. So typically in these critical space applications, we want to try our best to minimize the servicing requirement to allow the facility to have more time to focus on those critical operations. So again, I totally understand that depending on the application you're working on, servicing is typically still going to be scheduled by the facility staff, but again, enabling them to take some of that time back and minimize the requirements is really important. So whenever you're selecting your air valve technology, I strongly recommend that you ask some clarifying questions to better understand your selected valve technology in consideration to servicing. So some questions you may want to consider are there access doors required for their valve? Is it something that's mandated that the valve will naturally come with, or is it something that's an additional option that you can purchase from the valve? If the valve comes with no access doors, does that tell us something a little bit about the technology required and its robustness over its lifetime? Additionally, you're going to want to consider what's the year-to-year drift potential of your selected transducer technology. If that drift potential is high, you might want to consider the fact of the re-zeroing and recalibration of that transducer over the lifetime of its operation. And then lastly, you still want to consider asking the question of what's the factory recommended service interval? Does the factory recommend servicing the valve on a set schedule, or does it let the facility dictate and drive that servicing schedule? So in a typical critical space application, in a very generic critical space application, I'll kind of summarize a little bit about the life cycle servicing required for the terminal unit, high accuracy terminal unit, and the venturi valve. So typically, because your terminal unit has the sensor ports facing directly in the airstream, you will see a lot more servicing required for that legacy terminal unit. For the high accuracy terminal unit, your life cycle servicing will depend about the technology you select. Some high accuracy terminal units will do better at minimizing requirement for servicing or minimizing the effect of dust, lint, and dandruff compared to other valve technologies. And then lastly, for a venturi valve, typically that life cycle servicing isn't going to be required, mainly for the fact that there's limited direct airflow measurement going on inside of that valve. So we'll go ahead and summarize everything that we've discussed in this webinar. So again, here's just a high-level summary of the valve technologies we've talked about in today's webinar. So again, our terminal unit and our high accuracy terminal unit are going to be pressure independent electronically. So you're going to have to provide a controller and an actuator in order to get us that pressure independence. Whereas a venturi valve is mechanically pressure independent. So it's going to mechanically regulate due to changes in that pressure in order to control airflow. Typically, your terminal unit is going to rely on velocity pressure. Your high accuracy terminal unit can rely on a variety of different airflow measurements depending on the technology you select. But for Antec controls, we do utilize differential static pressure readings. And then for your venturi valve, it's typically going to rely on an airflow measurement from the position feedback. So again, that's relying on that precise potentiometer to measure the position of the lever arm to give us the airflow feedback based off of the factory calibration and testing that the valve goes under. So the last two I just want to highlight here is two critical ones. Again, is contamination resistance and turndown ratio. So typically with your standard accuracy terminal unit, you're not going to get any ability for contamination resistance, and you're going to get the lowest turndown ratio. For the high accuracy terminal units, you're going to get some natural protection for the contamination resistance, depending on the valve technology and the manufacturer you select. And then again, we're going to get a higher turndown ratio between 11:1. And then lastly, for the venturi valve, we're going to get that natural contamination resistance due to the higher pressure and the lack of direct airflow measurement. And it's going to give us the largest turndown ratio starting at 20:1.